morning, everyone. Okay, how did the homework go? Please, as usual, start putting your questions on chat. Okay. All right. So we start with number 28. All right. So we have the integral from 1 to infinity of the tangent inverse of x over x squared plus 1 dx. All right, so this is different type of integral. So we have the limit, the interval of integration is inbounded. So it's from 1 to infinity. That's it, but that's absolutely an improper integral. And the definition, we have to be careful that whenever we have an improper, to evaluate it, we have to write it as a limit. So it's a limit of the integral from 1 to t of the tangent inverse of x over x squared plus 1 dx. So that's always have to be the first step. Okay, use a definition. Once we do that, the rest is basically finding an integral, evaluating this integral, when the upper limit is t. So the upper limit is a variable. All right. So now I have to focus on that integral by itself. All right. So I will do the antiderivative without limit, because this is not a clear antiderivative, and then I do the fundamental theorem. All right. How should I compute this integral quickly? What do you see immediately when you look at that? Are you guys with me? Can you hear me? You're very quiet. What do you see? How should we evaluate this integral?
Substitution?
Substitution, exactly. Because what do we see? I mean, it's almost like we see tangent inverse, and we see its derivative, 1 over x squared plus 1. So we're going to use the substitution. Let us say, so substitution. U equal tangent inverse. The du is 1 over 1 plus x squared dx. So it's very clear, a substitution problem. So it's going to be equal to, this is the du. It means a half u squared. It means a half tangent of x squared. Okay, so I've only evaluated the indefinite integral, and now I go back and I evaluate the improper integral. All right, so that will give me the limit as t goes to infinity of a half tangent inverse of x squared evaluated between 1 and t. So this will give me the following, equal to, a half is a constant, so I don't really have to worry about it, but let's see what I get. It's a half tangent inverse of t squared minus a half tangent inverse of 1. And I need to compute the limit of that as t goes to infinity. So let's see, this is equal to 1. All right, when t goes to infinity, when t becomes large, what's the tangent inverse of t? What happened to it? So what's the end goal? Basically, whose tangent go to infinity. That's really what it is. So tangent inverse of t as t goes to infinity, it means what is the angle whose tangent goes to infinity? This is pi over 2. Okay, because the tangent of pi over 2 is not defined, but as the angle becomes close to pi over 2, the tangent goes to infinity. So this is going to be equal a half pi over 2 squared minus tangent inverse of 1 is pi over 4. Okay, so finally I end up
I have a question.
pi over 4 squared. Yes.
I'm really confused on how you got the pi over 2 for tangent
You know what tangent inverse of t?
arcsine.
Yeah. Tangent inverse is the angle whose tangent is t, right?
Yes.
Let us remember a little bit the graph of tangent. It goes like that. The tangent inverse is, so this is 0 and this pi over 2. So the tangent inverse is actually the angle whose tangent is t. So if the tangent goes to infinity, if t goes to infinity, means the angle is going to approach pi over 2. So in other words, as t approaches, as theta approaches pi over 2, the tangent of t approaches infinity. Does this make sense from here to here?
Okay, yeah, that's starting to make more sense now.
Yeah, when the angle approaches pi over 2, the tangent really goes to infinity. Now I'm going really the other way around. Now when t goes to infinity, the tangent inverse backward is going to go to pi over 2. So as t goes to become larger and larger, the tangent, the angle, is going to come closer and closer to pi over 2. We're doing really backward. Okay, so when the output goes to infinity, the tangent, the angle, is going to go to pi over 2 of the problem. Okay, now let's look at number 30. Number 30. Okay, so integral from minus infinity to 0 of e to the x dx. Okay. Again, that's an improper integral. That's an improper integral. And this is from minus infinity to 0. So e to the x goes like this. That's e to the x. And that's the integral from minus infinity to 0. Okay, without doing any math, do you think it's going to converge or diverge? Without any math done.
Diverge.
Yeah, because. Yes, you're absolutely correct, because.
Isn't it just because the e to the x always raises like any power like super high?
Oh, sorry. I drew the wrong picture. My apology. No. That's e to the x. My apology. That's the area. All right, no, it will not diverge. My picture was misleading. All right, so let us evaluate this. So the picture was misleading. That's why I told you it should diverge, because it's an area. And by drawing this picture wrong, the area is definitely an infinite area. So that's why I told you you can look at it, but my mind was not clear. So now what we have to compute? We compute the integral from t to 0 of ex dx. We compute this finite integral, and then we let the t goes to minus infinity. Okay, so let's see, it's equal to what? So it's the limit as t goes to minus infinity of e to the x evaluated between t and 0. is equal to the limit as t goes to minus infinity of e to the 0 minus e to the t. So finally, I will get the limit as t goes to minus infinity of 1 minus e to the t. Another question, what happened to e to the t when t goes to minus infinity? Back to you. So this is e to the t. You start raising t to a large negative power. Large negative power. What happened to e to the t?
It's basically 0.
It acts as 0. Yeah, because absolutely it goes to 0. Because if you think about it, what kind of power are you raising t to? Negative power, large negative. So e to the minus 10, e to the minus 100, e to the minus 1000. So it's basically 1 over e to the 10, 1 over e to the 100, 1 over e to the 1000. This is definitely will go to 0. Okay, because it's a large power, but it's a negative large. So e to the minus 10, that's 1 over e to the 10, and so on and so forth. So this will give me, honest to goodness, equal to 1. And the integral converges. And it converges to 1. It means its value is equal to 1. Okay, so here we have to be very careful, e to the t, because we're going to minus infinity. So the powers are actually negative, negative, negative. So it's 1 over that, which is equal to 0. Any other questions before we proceed? Okay, now, the last idea we're going to talk about before your exam is the following. So it's along the same line, so that the notion, the title, it's still improper integral, but we are going to take a different type of improper integral. And the idea here, what we're going to consider is the following. So in the first part of the section, you don't have to write this, I'm just having to talk about it. We looked at integrals over infinite interval. Okay, so these are the integral we looked at from minus infinity to 0. Okay, so the interval is infinite, and then the problem will come, okay, what do we mean by integrating over infinite interval? It doesn't make sense because Riemann sum, which is the definition of the definite integral, you take your interval and you split it. And that's the idea. It doesn't work from minus infinity to 0. This area is quote unquote infinite. So we defined it to be, okay, say, all right, you compute from 2 to t to 0, and then you start letting this t. So once we find the area for every t, then you let your t go to minus infinity. So basically what we did is from minus 10 to 0, minus 100 to 0, minus 1000 and 0, and we started finding what this area is. So the first section was over infinite interval. Okay. Now we are going to consider integral over finite interval. The interval is finite, but the integrand, it means the function is unbounded. So somehow the function blows up on the interval AB. So let us see the scenario and let's see what we're going to do. So what do I mean by that? So let us consider the following scenario. Okay. So suppose my function looks like this. And there's going to be tremendous similarity between what we're going to do now and what we did already. Suppose this is my function. This is my A, and this is my B. Okay, and my function is unbounded in the following sense. So suppose the value here, and at B, the function can have an asymptote, for example, and the function blows up. That's what I mean by unbounded. And now I have an infinite area here. Absolutely an infinite region. The area doesn't have to be infinite, but the region is an infinite region. And the question is, what do we mean by the integral from A to B in this scenario? Okay. So let us note very well that the limit here of f of x, that's my function, as x become close to B, is equal to plus infinity. That's the scenario. It could go also to minus infinity, it doesn't matter. Now the B, and let's watch carefully what I'm going to write, limit as x goes to B from the negative. of x equal plus infinity. Okay, so now what are we going to define the integral? So this integral now is also called improper integral. So whenever at one of the boundary, the function itself, the integrand blows up, we also say that we have an improper integral. And how are we going to define this improper integral? By imitating verbatim what we did in the previous problem. Who would like to give it a best shot? Who would like to give me the definition? Totally inspired by what we did before. Anybody? How do you think we're going to define this integral? Give it your best shot. You guys are too quiet for me today. Okay. We're going to do the same thing we did actually yesterday. We compute the definite integral up to t. So we compute the integral from a to t. Up to here, the function is well behaved. We can use the notion of definite integral of f of x dx. So we compute the integral up to here, and then we do the same thing, and then we take the limit. When this limit here become close to b from the negative. So that's going to be our definition. So it's going to be we compute the integral from a to t, what t is a number close to b, and then we let the t goes to b from the negative. But before I give the whole slur of definitions, who can think of an example of a function that looks like that? Who can give me an example of a function that of an interval where the function blows up? It has the same kind of picture. So you don't have to write because we're going to do a lot, but I want you to interact with that. Who can give me a function that I say on the interval 1, 2? So I said the function looks like this. Who can think of a function that does this? X cubed? No. No. Why x? Because x cubed has no problem at 2. Keeps going like that. And if this is 1, this is your x cubed. If this is equal to 2, x cubed will be 8. I want it to blow up at 2. Because I want the function to go to infinity at 2. Yeah.
Could we
I want it to go to infinity. That's really my issue here.
Could we do x minus 1 times, or x minus 2 times x plus 1?
What do you think? Well, this function blows up at 2. It means when x becomes close to 2, what's this function? This function takes the value 0. I'm not going to have any issue. This is a typical parabola. I want the function to blow up here. It means I want it when we get, it's not, I don't want it defined at 2, so let me make it easier. And I want it to blow up to infinity at 2. What can cause a function to blow up?
Would it be like x cubed divided by x minus 2?
We're getting better. That's a better scenario. Do we need x cubed? Honestly, no. I mean, x cubed is not safe, but x cubed will do. Now we're having an issue. Now my function has an issue. That's the scenario I'm going to have. Now, when x becomes close to 2, and I'm interested in one side of 2, not both sides. So when x becomes close to 2, and from, let's see, which side here, from the negative, this becomes close to 8. If it's become close to 2 from the negative is 1.999. So it's going to be small negative, it's going to be minus infinity. But if I play a little bit with it, so I switch it around, minus x plus 2 is going to be plus infinity. This is exactly what I'm looking at. This is what I'm looking at. So the function is to be plus infinity, it's 2 minus x. Okay, that's a very good function. So that is f of x equal x cubed over 2 minus x. So that's a function where it's not defined at 2, and when we're becoming close to 2, the function totally blow up. Because what causes a function to actually goes to infinity at a value is what causes the denominator basically to go to 0. That's really what's happening right there. So now this is, when x becomes close to 2, the function is not defined. I have an infinite area. And so the question is, what do you mean by the integral from 1 to 2? And what we mean is exactly the following. We start computing the integral close to 2. So for example, we computed up to 1.9, and then 1.99, 1.999, and we see what's happening to those areas as we're getting closer and closer to 2. And the value we get is what the integral is. If it's finite, we will say a converge. Infinite, we will say diverge. That's the scenario we're looking at. All right. So now part 2 is the same idea, but we can let the function blows up at the limit from the left at a. So the same scenario here. But suppose the function blows up here. So at a, we have an asymptote. So the function is not defined here, but it's nicely behaved at b. So my function can look something like that. Okay. So in this scenario, we're going to note that the limit as x become close to a of f of x equal plus infinity, and x become close to a from the right, it means a plus, a from the positive. And in this scenario, the integral is defined to be the following. The limit as from, I don't know, you finish what I'm writing. You should have the picture in your mind.
From t to b.
From t to b of f of x dx, and the limit of what? What do you want t to do?
T approaches a from the right.
T approaches a from the right. Okay. Well, last scenario is the following. So these are problems with the integral. So you have an integral here, but this integrand have issues at the upper bound or have issue as the lower bound. So the function is unbounded. The notion of, so we have an infinite area. That's the, so the question is, what do we mean by this integral in that scenario? So the last scenario is the following. And then 3 is the following scenario. Actually, probably I should finish this piece here before I move to my last scenario. So in this scenario, we can say, so like I did last time. So here I write, we say that the integral from a to b of f of x dx in both cases converges if the limit exists as a finite number. It means it's not infinite, exists as a finite number. So like in the previous section, we said that the integral converges if the limit exists as a finite number. Otherwise, we say it diverges. We say the improper integral diverges. Okay, I read it again. So we say that the improper integral from a to b of f of x dx converges if the limit exists as a finite number. Otherwise, we say the improper integral diverges. Now the last scenario. Okay. The last scenario is the following. Sometimes you will encounter the following problem. A, B, and the function blows up not at the end point, it blows up in between. So this is my function here. Go like that. Doesn't have to be in the middle, but somewhere between A and B it blows up. So now here again, I have absolutely a problem. I have an infinite domain. So what we are going to say in this case, so here we have the function which is blowing up in the middle. So in this case, if the improper integral from A to C of f of x dx, if this integral and the integral from C to B, the separate one, converges, if both converge, then we say that the integral from A to B converge. And we write that the integral from A to B is the sum of them. Just like we did yesterday between minus infinity and infinity. Now, if either diverge, we say the integral diverges. Okay. So before I give you example, I'm gonna go back to you and I want you to give me example of this behavior. Right. So you gave me example of this behavior. Now I want you to give me the example of the last behavior. So will give you the interval. This is 1, I don't know, this is 4, and 3 is somewhere here. And I want you to give me example of a function which is nicely behaved, except at 3, where it blows up. So I want an example of this behavior. Okay, who can give me an example where the function behaved nicely everywhere, but it has an issue at one point? It's not hard. Come up with an idea.
Would you x over x minus 3?
X over x minus 3, for example. Okay, this function will definitely is defined everywhere except at 3. It blows up at 3. It definitely blows up at 3. It blows up this particular function that you guys gave me. Let us evaluate the limit when we're coming close to 3 from the negative side. It means x is slightly less than 3, is 2.99. This is going to go to minus infinity. So this function is going to look something like that. It's going to right here from the negative, it's going to go down. If I evaluate the limit from the positive, it means I'm going to let x become slightly larger than 3. So slightly larger than 3, this is going to be positive small. So it's going to be plus infinity. So this function is going to go somewhere like that. And this is at 1. So I have definitely a mess in my hand. And the question is, what do you mean by this integral? I mean, you have, this is blowing up here. So this could be plus infinity, I don't know. Minus infinity, I don't know. This could be plus infinity. So what is really meaning for that? And the meaning is, if the integral from 1 to 3, this one converge by evaluating it as limit, and this one is finite, then we say that the whole thing is finite. If one of them blows up, then we stop, the whole thing diverges. That's really the idea. So now I'm going to take examples of integrals, improper integrals of this type, where the problem occur either at the right endpoint, left endpoint, or in between. And because That's what's going to happen. So I'm starting with example, and every example I have, even though the beginning will be very simple, you have to tell me, is it an improper integral? What caused it to be improper? So example number 1. Suppose I tell you find the following integral. If the integral diverges, that's usually my question states so. So integral from 0 to 1, let us say of 1 over a cubic root of x dx. So question number 1, is this an improper integral? Is this an improper integral? Before we go any further. So improper integral are those integrals either integrating over infinite interval or the integrand itself blows up, is unbounded. This is what improper integral, inside the interval 0, 1. So is this improper, yes or no, and why?
Yes, because it blows up at 0.
Right. This function here is f of x. So here, before we even move any further, let us know that f of x equal, remember, a function behaves badly when the denominator is 0. So we note that f of x equal, if we look at the function f of x equal that, so then we know that f is not defined at 0, obviously. And the limit means when we're becoming close to 0 of 1 over cubic root of x become close to 0, and this go to infinity. Okay, so this is improper integral. So first we established it as improper. Otherwise, we don't need all this stuff. So we established as improper. So now the question, is it convergent or divergent? So the graph is always, this is 0. If you graph the function, this is the graph, this is at 1. If x is 1, f of x is 1. So this is this infinite situation we're dealing with. So now does it converge or diverge? Now I have to go back to the definition. Integral from 0 to 1 of 1 over cubic root of x dx. Before we even evaluate it, I'm going to write it as a limit of. Okay, who would like to tell me what limit? Very precisely.
Isn't it going to be limit of t gets to 0 on the plus side?
Yeah, exactly. And the integral is from where to where?
T to 1.
T to 1. Of 1 over x, cubic root of x dx. So first we have to write it as a limit. Once we do that, and then we're basically in familiar territory. The only thing is that we have to find an integral that deals with a t. The answer will depend on the t, and then we have to let the t goes to 0. So that's really the idea. So let us evaluate this integral. The only way to evaluate this integral is we have to rewrite it as x to the minus a third dx. Okay. So this will become equal to antiderivative of x to the minus a third is 1 over minus a third plus 1, which is 2/3. So this will give me a 3/2. X to the minus a third plus 1, which is going to give me 2/3. Between t and 1. We evaluate. We have no way out, and then we're going to let t goes to 0. So we're going to evaluate very easily. So it will give me the following. Oh. 3/2 at the upper limit is 1 minus 3 over 2 at the lower limit is t to the power 2/3. So now what's going to be the limit? As t goes to 0, that's a constant, remaining constant. So when I start taking values of t closer and closer to 0, t to the power 2/3, remember 2/3 is a positive power, so this will also goes to 0 because it's a positive power. So this is going to be equal to 3/2 minus 0, which is equal to 3/2. It means the integral converges the integral converge, and the integral, its value, so by the definition now, its value is equal to 3/2, and that's the value of this integral. It means that this area down here, this area here, even though the function is blowing up, but it's not blowing up fast enough. It's not really blowing up fast enough. We still have a finite area. So it's very counterintuitive. That's why the math is crucial. So it still is an infinite area, but it's not blowing too much to infinity. So this is equal to 3/2. So the area is 3/2. So as I said, those ideas are a bit counterintuitive, because if you look at this, you say, you know, it's blowing up, so the area has to be infinite. But actually, it doesn't blow enough fast enough. That's really the story. All right, so let's do 3 more examples along the same line. So example number 2 and 3, and suppose example number 2, again, simple scenarios, integral from, let us say 1 to 3 of 1 over, basically I'm spelling it out for you, dx. Again, is it improper? So you don't even start doing thing unless you make sure it's improper, because otherwise we don't need to do this limit. Is it improper? Yes, no, quick. Means do we have issue here? Go ahead. We have, yes, with the upper limit, absolutely. If we look at the function f of x here, usually you take the function and you look at its denominator. And you ask yourself, when is the denominator 0? Because that's really where the problem is. And here the denominator is 0 when x equal to 3. And then you look, is it part of my interval? And definitely it is part of my interval. So this is my integrand. We see f is not defined when the denominator is 0, right? When x minus 3 squared equal to 0. That is when x equal to 3. And the question is 3 part of my interval? Yes, which is the upper limit. And so moreover, so we have now, so basically we always say, okay, we look at the function, we look at this denominator. That's really what's going on. What causes a function to blow up is when the denominator becomes close to 0. And here the denominator becomes close to 0 when x is equal to 3. So, and we have that the limit when x becoming close to 3 of the function, this is equal to infinity. So the function does blow up at one of its limit. And graphically, this is going to be the picture. This is my 3. My 1 is here. At 3, the function, that's because it's a square here, is going to go to plus infinity. And at 1 minus 3 is going to be 1/4. That's again going to be my graph, if I graph it correct. That's my infinite area. So now we have to compute this. So we use the definition over and over the definition. So that's the limit of from 1 to 3. So this is my t here. It's wrong. It's blowing up here. So I computed it from 1 to t. So you don't have to memorize the definition, you just have to understand it from 1 to t. And then I'm going to let this t become close to 3. And from the right or from the left? Quickly.
Negative.
Negative. Okay, so no memory, it's just looking at the picture and proceeding. So now the question boils down to find this antiderivative, okay? And then use the fundamental theorem. Okay, so I will do this usually in those problems to make life easy for us. I evaluate the indefinite integral by itself, and then I go use the fundamental theorem. So first, let me focus on that. How can I find the antiderivative of this very quickly?
U substitution.
Let's say U
X minus-
substitution. Absolutely. Absolutely correct. is the x. So this would give me 1 over u squared du. That's not a natural log. Be careful, you sum of u still give me a natural log for that. And this is 1 over minus 2 plus 1, which is minus 1. U to the minus 1, it means minus 1 over u. It means 1 over minus 1 over x minus. All right. So finally, this is going to give me become 2. Now I go back to my original problem. I found the antiderivative. Now the fundamental theorem of calculus tells me that it's my antiderivative evaluated between 1 and t. Now minus is, we can actually factor it out if you want. So I end up with the limit when t become close to 3 from the negative of. Okay, I will have minus 1 over t minus 3 minus minus plus. At 1, I will have 1 over minus 2. Too many minuses in this problem. Very good. Now, what's the limit of that? Now, it's your job to tell me what happened when t become close to 3 from the negative. Analyze it.
Doesn't it become 0?
What becomes 0?
Well, when you subtract like t coming from t equals 3 to the minus side, minus 3, doesn't it become 0?
What it? The it stands for what?
Well, the solution, like t minus 3.
Yeah, so this will come close to 0. Is it positive or negative 0?
Negative.
Negative. So it's become small and negative. What about the whole expression now? That's this one. So what you said to come close to 0 is this piece, right? That's become close to 0. I have 1 over it. What will happen to it?
Just becomes 0.
No, think again.
Divide.
Let me write it bigger because it's not big enough, I think, the way I have it. So let me write it big. It's the limit as t become close to 3 of minus 1 over t minus 3 minus a half. Okay? So what will happen here? When t become close to 3 from the negative, this piece here becomes small, very small, and negative small, because it's 2.999. But that's the denominator. Now you're having 1 divided by something very small. This would give me what?
Infinity.
Defined.
Infinity. Infinity. Remember, think about it. 1 divided into very, very small number. So if you ever forget, do it. So divided by 10 to the minus 1, 10 to the minus 2, what you get? 10. 100. It gets larger and larger and larger. Okay, so if you have, or mathematics, if you have something of length 1 and you divide it into tiny, 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 tiny pieces, you're going to get a lot of pieces. The tinier, the more. The tinier, the more pieces. Or you can think about it this way. So this is going to blow up to infinity. Now, is it a positive or the negative infinity?
Positive because it's a negative over a negative.
Right, it's negative over negative, positive, infinity. Okay, so do those limit very, very carefully. We are heading toward limit. And if we're not doing those one, we're going to be in trouble. Okay, so now finally, let me put the whole problem together. This is going to go to plus infinity now. And this is minus 2, which is equal infinity, and the integral diverges. So as I said, without doing the math, without doing this, there is no way we know what's really happening for those integrals. That's why we know we need the math to do it. So in this case, it means this area is actually infinite. What's happening that this function blows up fast, very fast. So the value are going to be becoming larger and larger and larger. Okay. All right, we're gonna do 2 more problems along the same line, so you guys will be very comfortable with that. So I'm gonna take the following. Suppose the same type of question, evaluate the integral if possible. So suppose I take the following, integral from, sometimes we don't see the integral as pi over 2, for example, of d theta. Okay, and the question is this an improper integral? Yes, no, justify. And then once we decide,
Yeah.
the question is, as it converge or diverge?
Won't it blow up at pi over 2 because sine of pi over 2 is 1?
Exactly, we have a problem at pi over 2. So is it improper integral? I ask myself, all right, so my function here, I called it f of theta, is cosine theta over 1 minus cosine sine theta, sorry. And the problem really occur when the denominator is 0. So you ask yourself, okay, when is the denominator 0? When sine theta equal to 1. Now our trigonometry would tell me that this happened at pi over 2, at 3 pi over 2, and so on. But in the interval 0, between 0 and pi over 2, the only value what it will blow up is at theta equal pi over 2. So now when theta become close to pi over 2, from the negative here, because I'm working from 0 to pi over 2, so I'm interested what's happening from the left of the function. It's going to be equal to what's going to be this limit? I should have thought more about that. What's going to be this limit? Anybody can compute this limit for me?
0.
Because
The cosine over 2 is 0.
yes, how about
And
the
0 over
denominator?
anything is 0.
No, no, no. When theta become, the numerator become close to 0. What about the denominator?
Oh, that'll become 1 or no, sorry, 0 then
So
as well.
0 over 0 is what? Let's remember calculus 1. 0 over 0,
That'd be infinity.
no. Can you help? Is 0 over 0
Undefined.
infinity? All of you, is 0 over 0 infinity?
It's undefined.
It's in indeterminate form, right? Because if you take a small number, let me take to the minus 10, very small. I divide it by a smaller number. Okay, what type of number do I get? Large or small? In this scenario,
Large.
large. In this scenario, we get large. If I flip, both are small, but this is way, 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 way smaller. I'm going, which is small. Okay, so when we have 0 over 0, this is called indeterminate form. It means the answer really depends on how the function going to 0. Now, how do we do in this scenario to find the limit? And in this scenario, when we have 0 over 0, L'Hopital's rule come to the rescue in this situation. Okay, so whenever we have 0 over 0, L'Hopital's rule, so this tells me that the limit of the derivative of the numerator, so I wasn't planning to go that route, but I did, over that. So it's going to be the limit of derivative of cosine is the minus sign. So whenever I have 0 over 0, that's in indeterminate form, and that's really where we have to use L'Hopital's over 1 minus sine. So the derivative of that is minus cosine. All right. So it's going to be what's going to be the limit. Now, when theta become close to pi over 2, this is going to become close to minus 1, and we want pi over 2 from the negative. And the cosine, when we get close to pi over 2, this is my cosine. This is my cosine. This is my pi over 2. When we get close to pi over 2, the cosine is going to become close to 0, but it's a positive 0. Then this is going to become close to, so that's small, but do not negative, small negative. And finally, I will end up with minus 1 over something small but negative, which is going to give me plus infinity. So the function definitely is going to blow up at one of the limits. Okay, so I repeat the process. I try to ask myself what's happening near pi over 2, because I know something should happen. The function is not defined at pi over 2. So I try to evaluate the limit of that. So I get that the numerator goes to 0, denominator. 0 over 0 is an indeterminate form. It could be anything. It could be 1, 2, 3, 0, or it can blow up. So I have no idea. I need to use L'Hopital's rule. So it's the limit, it's derivative of the numerator over denominator. I did that. So I'll have sine over cosine, and then I study. When theta becomes plus pi over 2, the sine goes to 1, the minus 1. The cosine becomes very small, but it's positively small because we're approaching pi over 2 from the left. And small but negative, small but positive, with the minus here, small negative, then I will have infinity. My function absolutely blowing up. So now to find the antiderivative, so to study the integral, is definitely a limit problem. So now let's do that. So now we first start by writing the definition. We don't really evaluate anything except, one of your classmates asking me, it depends on how fast the numerator and the denominator goes to 0. That's really the issue. And L'Hopital's rule helped me to get rid of that problem. So first we have to write the idea of the limit. So that's the limit. There is no problem at 0. The problem is at pi over 2. I introduce my t. And then this would give me cosine theta over d theta. And then my t has to become close to pi over 2. And then I stop for a second. Is it from the right or from the left? If my interval is from 0 to pi over 2, it means I am approaching it from the left. So pi over 2 minus. So first the setup. Once as I finish the setup, now I have to find the antiderivative. So I have to integrate cosine theta. So I do the indefinite integral first, just to make, so I don't have to deal with the limit at the beginning. Okay. All right, so quickly, how do we find the antiderivative here? Oops, time is up, I'm sorry.
Substitution.
Yeah, I'm sorry, I didn't pay attention to time. I got caught up with that. Then quickly, the du is, the derivative of sine is that. So this is gonna give me the integral of cosine theta d theta. So 1 over u du minus ln of u minus ln of 1 minus sine theta. So I need a minute and then I'm done. So now I finally go back to my integral. That's the limit. As t become close to pi over 2 from the negative of my antiderivative, evaluated between 0 and t. So finally, I'll get the limit of minus ln of 1 minus sine of t minus, okay, I put minus, plus ln of 1 minus sine of 0. Okay, so I will rewrite this one big, and then we analyze the limit, and we will be done. So t, so I'm going to rewrite it, nothing really. It's a 1 minus the sine of t plus 1 minus the sine of 0. Now the sine of 0 is 0, but I will write this in a minute. Now analyze that, and we'll be done. Analyze it for me. Okay. What do I mean by analyze it? When t become close to pi over 2, sine of t become close to what?
1.
1. So this become close to 1. Not equal 1, because t is close to pi over 2. T is never pi over 2. So this is going to become close to 1. So this piece inside the log is going to become close to what? Inside the log, become close to what?
0.
0. Close to 0. As I repeat, it's never 0. It's close to 0. So if you guys write ln of 0, I scratch it because we're close. The limit, we don't never take t pi over 2. We're taking t close to pi over 2. And now finally, remember the graph of the log. That's the natural log that we should know the graph. So when the input becomes close to 0, what happened to the output of the log?
It gets closer to negative infinity.
It becomes close to negative infinity. Absolutely correct. So this whole piece here now, so as you realize, I do it piece by piece. This is going to go to plus infinity. And here ln of 1 is 0. So this is going to be equal to plus infinity. So you have to evaluate your limit very, very, very carefully. So the integral diverges. End of the problem. Okay. Sorry for keeping you up so much. All right, so for tomorrow, your homework is on bright space. You do it. And please, I hope you guys started your review. I know some did. And tomorrow I will answer any questions you have, and I will address some of the issues that you guys had previously. All right? Okay, time, of course, time is up. Class is dismissed. I have office hours right now. Anybody has questions, please feel free to come. Bye-bye for now.
Have a good day.
Thanks.